My name is Henok Desta, and here I'll be presenting the Oscillations lab for Physics 1. So the purpose of this experiment is to analyze the motion of a mass oscillating in both the x and y direction, compare it to that of a computational model, and calculate the change in energy of the system. The brief preview of the results shows that the experimental data and the computational model have similar but not identical data. The energy principle was satisfied as the change in energy of the system was found to be zero. The first fundamental principle that is vital for this experiment is Newton's second law, which states that the net force is equal to the derivative of momentum over time, which is another way of saying it is equal to mass times acceleration. The net force is also equal to the overall sum of all forces acting on the system, which in this experiment is just gravity and the spring force. The force of gravity is equal to the negative of mass times gravity, and the spring force is equal to negative k times change in s times L hat. Another important thing to know for this experiment is the energy principle, which states that all energy in the system will sum up to zero. For this lab, there is kinetic energy, which is equal to 1/2 mv squared, gravitational potential energy, which is equal to mgh, and spring potential energy, which is equal to 1/2 k change in s squared. Knowing all of these will be a big help when creating the computational model. Other relevant formulas include the velocity update formula and the position update formula. In this experiment, my system was the mass, spring, and earth, and there were no surroundings considered. The initial position of the block was negative 0.118, negative 0.6260 meters. Its mass was 0.402 kilograms, and the velocity was 0 meters per second. The stretched length of the spring was 0.7 meters, and the relaxed length was found to be 0.127 meters. Lastly, the spring constant, K, was calculated to be 6.88 Newton meters. The graphs on the right show how the mass moved in the x and y direction as time passed. The initial position, mass, and velocity for the computational model created in GlowScript were set to be the position, mass, and velocity seen in the experiment, which were negative 0.118, negative 0.6260 meters, 0.402 kilograms, and 0 meters per second, respectively. The spring constant was set to 6.88 Newton meters, L naught was set to 0.127 meters, L was set to the position of the ball minus position of the spring fixed attachment point, and L hat and S were found using everything else. Kinetic energy, gravitational potential energy, gravitational spring energy, and total energy were found using the formula shown previously. The same goes for the gravitational and spring forces and the net force. The position and velocity update formulas were used to change the position and velocity of the ball for every iteration, and the spring's values were updated using their own equations. Lastly, the kinetic, gravitational, and spring potential and the total energy were updated for every iteration using the previous formulas, and how they changed was calculated by simply subtracting initial values from the final. So as you can see in the position graphs for x and y, the experiment ones look very similar to those of the computational model, although they are not identical. We can see that as time goes on in the experiment, it starts to get further and further away from the points seen in the computational model. This is due to the fact that this is in the real world and not a closed system, which leads to other forces being applied onto the system by things like drag. Potential errors in this lab include three main ones. The period of oscillation was calculated using y time values, which will lead to different results compared to the x time values. Manually placing tracker points could have led to a slight inaccuracy for the actual position of the mass. Additionally, there are other forces acting on the mass that are not included in the experiment, which means that the data is likely a bit incorrect. So the energy principle was satisfied for this lab. Its conditions are met if the sum of all the energies in the system equals zero, and it's shown in the graph that the change in energy stays at zero throughout the duration of the experiment, meaning that the sum is in fact zero. As you can see, the period for the x positions was calculated to be 1.614 seconds, and the period for the y positions was equal to 1.519 seconds. The difference seen here will result in varying calculations for the spring constant, leading to a difference in initial spring length as well. So, in this lab, I analyzed the motion of a mass oscillating in both the x and y directions and compared experimental data to a computational model. The energy principle was satisfied for this experiment as the sum of the energy in the system was equal to zero. In the real world, systems are not usually closed, so it's hard to control or predict every force being applied on the system, leading to varying data. Thank you.